Okay, so today I'll talk about analytic continuation on domains of C to the n, focusing on the case where n is greater or equal to 2. The case n equals 1 you learned in your complex analysis course. So first I'll recall the definition of an analytic function on C to the n. Next, I'll state the main result of this short lecture, the Hartogs extension theorem. And then to prove the Hartogs extension theorem, I'll need to get a little bit into the Delbar problem in C to the n, which has its own interest. And then once we have some information from the Delbar problem, we'll prove the Hartogs extension theorem at the end of the lecture. All right. So let's start with the definition of analytic functions in C to the n. So pick an open subset of C to the n. We say that a function from omega to C is holomorphic or analytic, and the abbreviation for this will be F element of curly O omega if F is C1 in omega, so it's differentiable and its first partials are all continuous. And moreover, all the first order derivatives in the DCJ directions are 0. So all these Cauchy-Riemann operators J. So it's fair to say that you're holomorphic if you are continuously differentiable and holomorphic in each direction separately. Now, let me just make this quick remark here. You can quickly skim through this information in your favorite several complex variable textbook. I like the one from Hormander, that just from this definition, you can easily deduce the multivariable version of the Cauchy formula. Holds, and the same way as in one variable, the Cauchy formula on the disk immediately implies that holomorphic functions have a local power series expansion. And if you have a local power series expansion, that means that automatically you will get an identity theorem, that if two holomorphic functions are equal in a neighborhood, then they have to equal everywhere. And then what else? There's all sorts of these results. Also, from the Cauchy formula, you automatically get, by differentiating the Cauchy formula itself, that being analytic implies that you are smooth. So infinitely many partial derivatives exist. All partial derivatives exist. Okay, so without further ado, let me quickly state the main theorem for today that is due to Hartogs. This theorem of Hartogs says if, again, you have an open subset of C to the n, which is, I suppose, connected. Yeah, you don't need connected, just open is enough. And pick a compact subset of omega. All right, so now pick next a holomorphic function on omega minus k, right? So you use k to punch a hole in omega. So pick a holomorphic function O on omega minus k. Then here's the punchline. So there exists a function holomorphic on the big omega such that f restricted to omega minus k, capital F restricted to omega minus k is nothing but small f, right? So what this says is perhaps a surprising fact, if you hear it the first time, that in case where n is greater or equal to 2. So this is very important here. I forgot to emphasize it. I should have started with this. So if the dimension of the Euclidean space is greater or equal to 2, then holomorphic functions extend over compact sets, right? So if you are holomorphic on omega minus k, then you can find a holomorphic function on omega that extends your original function. So as we know, in n equals 1, this is simply not true. Not true due to the fact that we have this Riemann extension theorem that sort of has a whole, sort of gives you a case study of what type of isolated singularities you might have, right? So in case k is a single point, right, then you know from one variable calculus, holomorphic calculus, that the singularity might be a pole, might be essential, or might be removable. Here, in dimension greater than 1, we learned that every isolated singularity is removable. So maybe that should be a remark here. If n is greater or equal to 2, then every singularity is removable. So somehow this Riemann extension theorem does not have a really good analog in higher dimensions. Okay, so what sits behind this phenomenon? So the rest of the lecture will focus on giving an argument for this Hartogs theorem. So we need to digress a little bit. So let me start with a digression. And this digression will be, as advertised, the Delbar problem. Oops. So start with a smooth complex valued function on omega. So what one can do, you can define the Delbar operator. The Delbar operator is something that closely resembles these Cauchy-Riemann operators here. So Delbar of G is nothing but del G del Zj bar sum from 1 to n, where dzj bar is nothing but dxj minus I. So what you're dealing with here is nothing but a complex valued one form. So this is a complex one form that we write in this very specific form. Now, really, the kicker here, and again, going back to the definition of analytic functions here on the left, is that a smooth function is analytic if and only if del bar of G is identically 0 on omega. Okay, interesting. So let me start over here. So what's the Delbar problem about? Okay, so now suppose you start with the following setup. So you suppose you start with a holomorphic one form of this type. So let's call it just simply F. So sum of Fj dzj bar, where the Fj's are smooth holomorphic functions. And I will just deal with the case where these Fj's are actually compactly supported in in omega. So that will suffice for today's lecture. And when solving the Delbar problem, what you want to do is, given such a such a complex valued one form, you want to find another function in omega such that del bar of G is equal to F. So now if you write things out, right, by definition, this should be equivalent to simply asking what? So sum of del, oops, sorry. Now, after identifying coordinates, you can further say that this is equivalent to, so find a G in C infinity omega such that del Gj del Zj bar is equal to the Fj, right? Obviously on omega. Now, what you notice immediately that this system of equations, right? So you have n equations here, is overdetermined, and you need to have some constraints here on F. So need some constraints on F, namely, right? So to start with, you know that you can take partial derivatives in any order. So in particular, if you take a partial in the Zj bar direction and then a partial in the Zk bar direction, it's the same as taking a partial first in the Zj direction bar and then a Zk bar direction. So in particular, right, if this equation holds, then this implies that del Fj del Zk bar should always equal del Fk del Zj bar. So you do have this sort of trivial constraint on your one form. And yeah, so let's see where we are with this. So the next theorem says that just with this trivial constraint here, let's call it star, you can always solve this Delbar problem. So let's call this Delbar. So theorem says, so pick a compactly supported complex valued one form of this type. So where Fj is compactly supported, moreover, star holds. So then there exists a G smooth function on let me make this as simple as possible. So let me just forget omega altogether in this theorem, and then let's just work on c to the n. So let's work on the trivial case where omega is equal to c to the n. This will suffice to prove Hartogs theorem. So then there exists a G compactly a smooth on c to the n, solving the Delbar problem. Moreover, and this will be the kicker, if n is greater than or equal to 2, so if the dimension is at least 2, then actually G is going to be compactly supported with support of G being included in the support of F. So on places where all the Fj's are identically 0, the G will be identically 0 as well. Okay, so let me quickly say something about the proof of this result. So the proof of this result is deceptively simple in certain aspects. So let me say, what do I mean by that? Right. So it turns out that you can actually guess what this G is. So you can pick GZ to be this interesting looking expression. So you take the solid, So the solid integral over C of the following expression. C2, Cn, d psi, psi bar. Okay, so psi here, psi here, psi, and psi. So you have a solid integral in psi, and you just integrate psi in place of the first coordinate of f times this Cauchy integral, Cauchy type integral kernel. Now again, when we say z in n dimensions, we mean a vector with complex coordinates, right? So really, it's interesting to show that GZ actually solves Delbar. So sorry, and not F here. I just mean F1. So you just integrate the first coordinate function of your complex valued one form, and that miraculously will give you a solution of Delbar. So let me just say here that you can show that Delbar of G is equal to F. So here you will use the fact that we have this compatibility condition here on the left. And what the other thing that you have to use is just this so-called Cauchy-Pompeiu formula. So this uses so-called Cauchy-Pompeiu formula. Maybe I just want to give you a reference where this is written out. So for example, you could look at Theorem 231 in Hormander's several complex variable textbook. So Hormander several complex variable textbook. The point I want to emphasize on is this sort of second fact here, which is going to come in. So if n is greater than 2, I want to argue that this GZ is going to have compact support. So why is that exactly? Let's take a look. So since F1 has compact support, right? So since F1 is compactly supported in C to the n, what do we know? Well, this means that for some big enough C, right, we have that if Cn, so the last coordinate, is greater than C, then we must have that F1 of psi Z2 Cn is identically 0, regardless of what the other coordinates are. Now, if we compare this with the way I define GZ, this implies that GZ is also going to be 0 if the last coordinate has absolute value greater than some big constant C. Okay, so what does this mean? Well, we also know that G solves the Delbar problem, right? F is compactly supported. So we get that by definition of holomorphicity, right? We get that G is holomorphic on Cn minus the support of the F. Okay, so you have a holomorphic function that is identically equal to 0 on some open parts of this set, right? So that means that by the identity theorem, we immediately get that G has to be identically equal to 0 on this set. So on Cn support. All right, so with this result proved, let's get back to the Hartogs theorem and see how the solution of the Delbar problem with compactly supported solution helps with holomorphic extension. Let's give here Hartogs theorem. Okay, so pick a holomorphic function on this note taker app, omega minus k. All right, so now pick a bump function on k inside omega. So let phi be a smooth, compactly supported function on omega, such that obviously phi is positive and phi restricted to a open neighborhood of k is identically equal to 1. All right, so now make this function f tilde, which is defined as follows. So it's 1 minus phi times f. All right, so by our construction, since phi is identically 0 near the boundary of omega, we automatically notice that phi is the same as, sorry, f tilde is the same as f near the boundary of omega. So in an open neighborhood of the boundary of omega, f and f tilde are the same. Okay, so now let's solve a Delbar problem here, and we will quickly see how useful it will be. So solve the following Delbar problem. Solve the following problem. So let us, so we want to get a function g, which is smooth and compactly supported in omega, such that del bar of g is nothing but Delbar of negative Delbar, so negative Delbar of f tilde, which is what? So which is negative Delbar of 1 minus phi times f. Now you can use the product rule here and you will get what? So f is holomorphic, so del bar of f is equal to 0. So you will get del bar of phi times f. So what's going on here? So phi is compactly supported in omega. So this thing, you can think of it as a smooth function on c to the n that's compactly supported. So by the previous theorem, we know that there is a compactly supported g solving this equation. So by previous theorem, g exists. Okay, so we want to solve both the Delbar equation and we also want to be compactly supported. Okay, so now we define f to be the following function. So we want f to be f tilde minus g. So this is obviously a smooth function in omega. Since g is compactly supported in omega and f tilde is equal to f near the boundary of omega, we also get that f is equal, so capital F is equal to small f near the boundary of omega. Moreover, let's check out what del bar of f is. So del bar of f is what? It's del bar of f tilde minus del bar of g. So by the solution of this problem, okay, let's see. Okay, so I made here a small mistake. So I need to get rid of this minus sign, as I'm sure everybody noticed here. Not everything is, nothing changes, but what you get if you do that is that here del bar of capital F is equal to 0, which implies that F is holomorphic in omega. Okay, so we have a holomorphic function that's equal to another holomorphic function on a neighborhood of omega. So by the identity theorem, we get that f is not only the same as small f near the boundary of omega, but actually has to be the same wherever small f is defined, which is omega minus k. Okay, so this gives us the proof of Hartogs theorem. Really, the focus is on not necessarily the statement, but how it relates to the solution of the Delbar problem with compactly supported solution, right? So that's the point where higher dimensionality comes into play, right? So unless G was compactly supported, this argument would not work. It would break down here. This would not be true. All right. Thank you for your attention and see you next time.